Okay, so we will today starting to talk about part 3, mainly about multimodal image and both for representation and for generation. So first we will talk about representation, which continue with the LLMs, text-based language models. Then we will talk about image representation, how to integrate that with text, and then we will start to talk about image generation. So, so today we will starting to talk about transformer-based image representation, mainly 2 topics, right? So let me see. The first time, just recall, particularly we will have a representation learning, transformer, and contrastive learning. So these are topics we already covered early in the lectures. Then specifically about the 2 papers today. One is VIT. So this is starting to become the standard representation for images instead of a CNN. It's already replaced that. So this is a essentially applied transformer to image representation. The second one is CLIP. CLIP is contrast learning. So the idea is to learn language and vision alignments. So basically, the idea is training with, if you recall, contrastive learning, which is a paper we talk about. They can learn representation, but more modern application of that is to this alignment of language and the image. And this one is resulting to this pretty well-known CLIP. There are other unsupervised image representation papers we do not have time to cover. So we will just focus on these 2 papers. Okay, so these are the backgrounds and what it is. The motivation. For the motivation, we just recall the few topics in the earlier lectures, and then we will discuss. If you recall, I think in the encoder-decoder lecture, we already mentioned, right? So there's encoder, there's decoder, there's a representation learning, there's generation. So encoder typically associated with the representation learning. Basically, it's a learn features that are used for downstream tasks, including generation, but also including like classification, regression, whatever other supervised tasks. So this is a representation. Particularly, we will talk about image, right? Transformer, of course, is a modern architecture for sequence models. Yeah, and essentially now it's taking over transformer, not only for sequence, also for image. This we'll see how it works for images. Contrast learning is a way of learning representations from unsupervised data. Basically, it's just a contrast. The contrast means, if you recall, related, unrelated views. And in particular, in the work we talked about before, related views can be generated by augmentation, for example, right? So, and unrelated views could be just generated by other data. So, so classical, that pipeline is a defined label, right? So such as ImageNet. This is like a CNN era. And then train with human labeled examples. After train with human labeled examples, then you predict on a fixed example at a time. The modern question, right, is slightly different. So this is like basically, if a label doesn't show up in your data set, you will not be able to classify, right? Later on, I think one clip come out, it's actually try to address the issue is actually can do arbitrary classification. It doesn't have to be pre-specified label. We will see why. There are two issues if we think about representation, particularly image representation. One is convolution necessary, right? Recall that we talked about the convolution that has been there around for many years, and before transformer. And the transformer certainly take over like the text. Then the question is whether I can do image. So this is one of the papers talking about. The supervision is, can we replace the fixed class label, enable zero shot transfer, meaning I can do arbitrary classification once I do this. That is actually the answer by CLIP. So these are two papers really broaden the application. So once you have to say, oh, I have to train a classifier for any special topics, later on, you don't need, you just do a very, very general representation, which can do classification. So basically, yeah, this is how we position these two papers in the framework of image representation learning, right? So essentially architecture and broad and fixed label classification. So general representation learning, if you recall that we already have that, right? I just use the same notation. So you have X is, let's say your image, because this lecture we talk about image. Z will be whatever representation. In both papers, it produces a vector, right? X to Z, Z becomes a vector. And then that basically this is an encoder, which is your representation learning based on. Desired property, and this is especially if you think about the contrastive learning, that is basically the similar semantics should have a similar representation, right? Then you have to interpret what it does that mean. This is where the contrastive later comes on. But in the VIT case, it's more about architecture. So in the CLIP case, it's about how to interpret this similar representation, and it's actually quite a useful thing. So today's lecture, VIT better encoder. Now I think it's already taken over. It's most, if people think about encoding image, they will think about the VIT instead of a CNN. So that's a current architecture. CLIP, better supervision signal. For visual, again, it's just the go beyond the fixed label. So we will see that actually in the notebook or when we talk about this paper, you can show that it actually can really classify arbitrary labels. Although we use a CIFAR as an example, but if you look at how zero shot prompt works, it actually do everything. So let's review quickly, talk about what we want to do with visual representation learning using transformer. So we just recall the transformer for sequence model, right? Transformer is a replace recurrent relation, RNNs, or with attention for sequence model. So it's all attention based. Why it's become so? Remember, there are two things we mentioned. One is long-range token interactions, right? So that's instead of a step. So you have a broader context. You will be able to deal with that. So if you recall the transformer lecture, this is what we talk about. The second one is training can be parallelized. So you can train with a lot of data. So this is two things which makes transformer popular. Yeah, so basically both are matters because even transformer, when you can parallelize the training, it can take a very long time if you think about that. So for the current models, the pre-training, right, it can take very long. It's 10 trillion tokens or more. So yeah. Long-range dependencies are easier to model. So this is basically, yeah, I think it's answer two. Maybe I'll remove this one, but basically this one says the same thing as that. If it works so well for tokens sequences in NLP, can we turn an image into a token sequence too? And do we really need this so-called inductive bias of CNN? So that's actually the question is talking about. This is basically the answer by this. You know, to be honest, this paper, it's a Google paper. It's using a lot of compute. If you think about novelty-wise, it really, you just apply this to vision, but it's very influential, means they actually answer the questions which for academic, if you do not have so large computation resources to train a big transformer for vision, it's very difficult to answer some questions, which is what we see later on, what they actually answer. It's really more to do with the scaling rather than anything novel in terms of architecture compared with the sequence, right? There's no special adaptation to vision almost. It just directly apply. But then, it is surprisingly successful. So, and this is basically becomes, if you look at, I think I don't remember, it's probably a clear paper. I don't remember. If you look at the reviews, they don't feel, it's novel, whatever. And yeah, but then it's the influence eventually is different, right? Because it answers some questions beyond just say technical novelty. NLP, a sentence sequence, word, subwords. This one is just a sequence of image patches. If you say a novelty, this probably is one, but even this image patch idea, I don't believe it comes from this particular paper. It's just they are using that. So essentially, image patch tokens. Okay. So yeah, this is how the whole architecture basically work. I can give a short conclusion to say, right? The idea is following. So this transform works so well, right? And also, if you think about the revolution of machine learning, in the early days, you use hand-picked features. They are handcrafted features. A lot of those sift feature. If you are really old, maybe 20 years ago, there's dominates the computer vision for more than 10 years. Until the CNN comes. CNN has some inductive bias, right? The shift environments and so on. But then, it's kind of prior, but then basically it's overtaken the handwritten. Handwritten, of course, is more prior. So CNN becomes less prior. If you think about the transformer, even less prior. Basically, it doesn't even encode any of these. It's directly models global instead of local. So it remove prior, but once the claim is once your data becomes so large, right, all the prior is actually not helping you. It's basically hurting you. So that's if you have one sense of the conclusion is that, okay? This one dominates because once you give you enough images, they will learn prior better than CNN, okay? Core idea. This is a mostly technical one, but it's just application. Remember, we are doing representation learning, so this is an encoder. So VIT, if you think about the transformer, there are encoder, there's decoder, right? So this is an encoder only for the representation. We could also use that for decoding. That will be talked about in next lecture, not this lecture. But for the encoding part, right? What you do is you are looking at this guy, right? This is 3 by 3, right? So basically, each patch, depending on size, you can say 2 by 2, 16 by 16, whatever. Basically, this is a small image patch. You aggregate it to be 3 by 3 patches. This is a higher resolution, but the 3 patches. Then you get this, right? So basically, you get here 1, 2, 3, 4, 5. Basically, you just go through. The position itself doesn't really matter much because the transformer, it doesn't care too much. So you have a sequence of these image patches. Each one you do a linear projection. Linear projection becomes transformer the input layer. It becomes a real representation of of your each image patch. Okay, so they start with that. Basically, linear projection of a flattened patch. Patch flatten is like this, and you do an image projection, right? And you have a position embedding. So, right, so basically this one, of course, we talk about this is absolute position embedding. There's no need for rope or whatever it is, because it's it's basically you just tell you each patch is where, right? So basically just each patch got a position embedding in the transformer input. Then getting this, you get you something input. Then you just go through transformer. Let's say this one is 512 dimension, right? Or whatever dimension, right? But this one, then transformer, you go to standard transformer. Up to the end, you also have these 9 patches, right? And then this will be 512. So basically, that each one is 512. You can, in some applications, the output of the final layer of transformers can be regarded as a patch of your patch representation of your image. Basically, you for example, each image is 9 times 512. Okay, that happens. We will see that when we talk about the VLM later on. And then next time, so that will be the way of how to represent the image. But for this class, they all come up become like this. It's just like a bird like a thing. So you have class representation because this one is trained on classification. VIT, the original paper, trained on classification. CLIP trained on image text alignment. And then other ways trained. But essentially, if you look at that, they just this is encoder, right? So essentially, you just have a classification head. Because encoder, they have a bidirectional attention. Doesn't matter where you put. You can put that at 0. You can put that at the end. It really doesn't matter. But here it's put at 0 and it comes out of class. So this is just standard transformer architecture, except you have if you say novelty is here. Is each image have a linear projection to the embedding instead of word, right? So you think about the word is word, it goes to embedding. This one image goes to embedding, and this is encoder only, just like BERT. It's an encoder only architecture, right? So basically, yeah. So that's all about the VIT. VIT is essentially this. Yeah. Yes. Question.
Projection and tokenization doing similar.
There's no tokenization. This is a continuous token. You can think.
Language and linear projection.
No, this transformer is completely separate from language. This one is a trained on image only. Yeah.
You have tokenization for images like small.
Yeah, this is VLM. So we will talk about the next class. Yeah. So the VLM will really combine this thing with language, and then you have actually VLM. There are even more recent development we will not be able to cover. Right? It's a omnimodal, or if you heard of that even more blurred. So. But essentially, yeah, you can do that. That's next class. But here, it just yeah, it's separate. But indeed, the question is right direction. It's basically you can have a unified representation. Yeah. There is one more question. I see. Let me see. How to determine how many patches are needed? This one I think basically this is a hyperparameter, just like yeah, each one is a one token. You can think about it. Each one patch is one token, right? It just goes to your embedding. If you think about the discrete token, you also need the embedding layer, right? It's just a discrete to embedding. Here it just continues to embedding. So that's only difference, but you can think that as tokens, yeah, image tokens. And this is actually the image token. This way is how it's used in VLM, which we will talk next time. Yeah. But anyway, so this is what it is. Split the image to the number of tokens is just hyperparameter. You depend on how do you train this. Usually it's a fixed resolution. You have to scale to that resolution to put this fixed batch, right, and to that. So essentially, but it's not a big deal if you scale to the resolution. It usually doesn't cause too much problem. Yeah, to fix the patch. I mean, for the ImageNet, usually it's a 224, right? So this is the overall resolution. Flatten each patch and the linear projective token embedding and add position and your learnable class token. And then once you have that, you get your class label. Okay. So this is basically, yeah. So this is a standard transformer encoder with bidirectional attention. Okay. So I think that's all I want to say about the architecture here. There really isn't too much about that, except you're just treating this one as a token. I think one thing the paper tried to say is the following, right? Is say basically this one specifically try to make it mimic the standard transformer. So they intentionally actually doing that, just doing minimum modification. What the minimum modification can do, the minimum modification is just replace your embedding using the continuous, right? But so they do a very minimum modification, and that's all. Okay. Okay, good. So this is this is about the transformer. So now let's basically talk about what their this is a little bit of technical detail, right? So image, you have this channel, this HW, and P is the patch size, right? Essentially, number of tokens will be image tokens will be this one divided by this square. So right, so this is pretty straightforward. Each batch is flattened linear, right? So basically, yeah, this is how it does that. Total token is n+1 because there's a class token at the beginning of just like a bird. It's very similar to bird, how they deal. Is there a clear separation between different rows of original image? I don't know what does it mean. It means this one doesn't care, actually. You just have, you can shuffle this actually if you want, because they only care about the position embedding. So you're starting from each row and going to next row, going to next row. If you think about the within each row, they do, because the position will be linear, so they do have separations. But for different rows, they just not getting together. Yeah. Directly analogous to NLP, right? So basically, words become a token embedding. Here is the image patch become token. So basically, minimum change is one selling point of this paper. Okay. Sequence length is number of +1. Okay. So I think it's just repeating. If you look at the encoder, this one just reviews recall this transformer architecture, right? So it really doesn't say too much. This is a residual standard layer norm, multi-head attention, right? These modules we talked about earlier, so we will not go over. Then you have a FFN, right? So basically, this is a MLP, one layer, and so on. Yeah, attention bidirectional because it's encoder. And the final representation, you have a layer norm of each one. They actually just have a 0. 0 means the class token, right? So this is for the original VIT, but for later applications, you could actually looking at all the tokens, okay? Or even you don't have a 0 token, that's also fine in the later applications. It doesn't have to have a actual token, right? Actual token is a little bit more, they are mimicking the bird, so rather than anything else, okay? But anyway, so I hope this got an idea. So the only thing you can remember is the image patch, and each patch gets one token. And otherwise, it's basically the same as a text transformer. Yeah, this key message is indeed mentioned in the paper. Is want to close to rather than invent a new thing. So basically say one universal architecture can fit it all. Basically can do whatever, right? Anything can be synchronized, right? So if you think about anything, even you say audio, you say whatever, speech, whatever, everything can be made a sequence. And then you just using the simple idea like this, then you can get a transformer. A little bit surprising is because actually that's what their intention. In some way, if you recall the scaling law, this is a test of scaling law in another way. I actually mentioned earlier, so CNN encodes strong image-specific inductive bias, right? Locality, right? And translation invariance, right? So they gradually form local image, gradually make it a global image. So basically, you always have this one. And they always maintain this kind of structure, windowed structure, right? So neighborhood, if you think about it, they always become a grid. Even they do downsampling. Upsampling is still an image. Image become image, become image. So this is something which is there. Essentially, VIT removes all. They just have an image patch. It still have an image patch. Within each patch, there is a locality. But other than that, it's not a lot of locality. Not a lot of locality. Okay. Attention is global. Actually, this is an advantage you think about. If you can remove all these inductive bias about CNN, no prior, so no fixed things. You do, instead of like CNN, you do local. Here I can learn global interactions. And this is why probably it does better when you have a large scale. Spatial structure is injected through patching and position encoding, right? Patching, of course, itself is local. So it does have some locality. But position embedding is the thing which gets you the global position structure. So essentially, yeah. But then that's all, right? So that's very minimum. So you just say different patches, you give a number, that's all. The model must learn much more from image structure directly from data than CNN because there's no this kind of prior, right? So basically, therefore you need more. Yeah. The main lesson, of course, is the following. So this is actually when you do the scaling law, when you do a lot of this machine learning, as I mentioned repeatedly, removing the prior, removing the inductive bias, make it more universal, more general, seems to win when the data become large enough. So this one is again verified. This is actually, you have to do with large scale. At that time, it's probably Google can do that, right? Or some very few companies can do that with large scale computing, and then they can answer these kind of questions. So they basically, as I mentioned, this is like a kind of a studying scaling law. The conclusion is in a smaller scale, CNN inductive bias helps, right? The larger scale, the CNN will not actually help you at all. The structure come in, or at least the VIT will take over. And certainly they can train with a large scale. That's why VIT becomes much more popular nowadays. They do have a better representation of images. Study pre-training on a data set of different scales. ImageNet at that, at the beginning, right, this is considered very large, 1 million, right? So when we started doing this GPU training, all this, but at the time, VIT, which is already 10 years later, this is a smaller scale. So they have much larger scale images. ImageNet 21, that's the full image data. So this is 20 million, right? And they have even larger. This is 300 million, right? So there are a bunch of. We also have other data which have hundreds of million, now even billions data, and at this scale, gradually starting from ImageNet to ImageNet and so on, gradually when your scale increase, the benefit of AVIT will show more. Main parallel pattern. This is the paper essentially have two things, if you recall. And one is just this architecture, which is simple. You just understand that the tokenization is different. That's all. Everything else is a transformer. The other one is this scaling, right? Scaling. Smaller data, VIT can be more overfitting. CNN inductive bias will win, but the larger data, larger VIT model will win, right? So after pre-training, VIT transfer strongly. Basically, they learn real good image representation when you're fine-tuning. And this one, of course, the original way to train VIT, right? So this one you can easily use for your image downstream tasks. But later on, there are some better ways to train. There are a couple of ways, but clip is one of the important way which we'll talk about later. This also can train VIT, and VIT will be able to use one. So VIT training recipe, this is on classification. Again, this is on classification only, this particular paper. Large data, right? So, the fine-tune on downstream task, a new linear classifier head, this is a typical way. People, in the older days, people just pre-train on ImageNet, and then fine-tune on other tasks. Here, you just say pre-train on larger classification data, fine-tune on the whatever tasks you have. Often higher image resolution than pre-training, but you know, this one depends on the task. Position embeddings are interpreted with resolution. So if your resolution, one thing is you always scale to the same resolution. If your resolution changes, you can also accommodate, basically. Yeah. Essentially, let's say I pre-train on 224, right? I will just fine-tune on 512. I can always interpolate this one to the other one and just fine-tune. Yeah. Yeah. So basically, this is scaling law. So essentially, this again is a repelling scaling law, and yeah, I think it's just repeating just again, but essentially using this data. So let's look at basically what they actually report, right? So what they report is this. Basically, you know, this is a number of. This one actually is already pretty large. So basically, if you look at this, already wins. Where is the C? Yeah, here is a ResNet. Okay, two ResNet. One is a very large ResNet, right? The other one is 152 is pretty large ResNet. Okay, this is ResNet 50 is more standard. It's a lot of people use ResNet 50. It's like this, right? So essentially, you know, if a VIT, if you look at that, even the largest VIT they played around, they have different VITs, right? Depends on the block size and so on. So this is a base, and this is a large model, and so on. So if you look at this VIT, the starting point, right, will be smaller. So even the smaller one, even not even not beating this, but then certainly not beating this. But gradually they are more aggressive. When the ResNet plateaued, this guys keeps improving. So essentially, you know, the point is they can scale once up to a certain scale. This induction bias doesn't help anymore when you have a 300 million scale, right? So basically, this is one thing to talk about. ResNet perform well with the smaller, and then VIT can take over when you have a large. So basically, yeah. So basically, you know, this is a key message which was talking about, and this one actually people buy because, as I said, nowadays people use VIT quite a bit. They used to use ResNet to be image representation, not anymore. Okay, if you the choice. VIT result scaling. This is another plot, right, which is basically aligned with flops of the to compare. Okay, and again, you just say, oh, this one has advantages, right? ResNet, it's a lower. This one's a higher, better performance. Performance result, basically compared with profs. They also talk a little bit about the hybrid. Hybrid is basically the following: generally perform well, at the same pre-training computing budgets, right? So essentially, this is hybrid means you starting with the ResNet. You extract some feature map and then on top of that doing transformer. So hybrid, of course, you also have some inductive bias. You can get better to start with, but eventually it doesn't really get too much advantages. Basically, all the inductive bias, all the things can be learned. So that's kind of a very interesting lesson. So, but this one is something people try to talk about in machine learning. All this knowledge can be learned as long as you have enough data. Okay, so basically that's what it says. To not be saturated. So yeah, so any questions at this point? This is essentially more or less what it is about this VIT. Okay. That's computing and so on. So let's go. This is a little bit past. I mean, we are not going to train on VIT. We just say there are available VIT from yeah. This one is one of the model you can do. Typically, you know, in this multimodal, you also have a processor in addition to model. This one just say processors. Because the image, you can scale that, you can do that. So it's like when you do data pipelines, we have this kind of special processors for pre-processor for data. Here is the same. You're always doing something, and then you apply to this model. Yeah, basically, you first have an image, right? You process that so that these guys can be applied with the VIT model. And then this I just say, okay, this doesn't do much. It just tells you, this model with this image inputs after the processing, you get this image feature. Okay, so this one is just the zeroth position. You could also return all the positions. All the position you give your the patch. Each patch has an embedding. Okay, so yeah, so this is how it's used. Yeah, we just need to know how to use, and you can fine tune that. You can do that. So basically, I think the homework probably it will be a VIT and clip. Oh, actually no VIT, clip, but a clip can use VIT, right? Clip VIT with clip, and also there's VLM question. Okay, so that's I think that's about the VIT. So I hope you know just two messages. One is tokenization of image. The second one is the scaling matters, right? So yeah, each patch nearly standard transformer is enough. CNN is helpful as only at small scale. So this is a quite an interesting lesson. Yeah. With enough pre-training, pure transformer becomes very competitive. This also, again, says transformer architecture really can learn very complex patterns, interaction patterns. So that's also another thing amazing in this term. Transformers is so powerful in trying to learn nonlinear interactions. This set of next paper, if AIT give a scalable image encoder, can we give it a better large-scale supervision? So this answers a different question. We will go beyond the fixed label to arbitrary so-called open domain classification. Basically, you can classify whatever you want. This is by through the image text alignment. And for the clip paper, they also deal with both ResNet and VIT, right? But essentially, if you look at the open clip and so on, if we do that homework, they are mostly using VIT representation. So you essentially, if you have a image representation, especially you want to align with text, right? And open clip, you extract that the image patches with VIT at the patch level. It will be a good representation. Basically, we will see that. So let's recall the contrast learning. So this one is looking at the image text alignments. Contrast learning is an unsupervised representation learning method that can scale. This is this CMC CLR, right, paper, right? Contrastive learning of representations. It learns representation. If you recall, I'm just recalling this, and then we will talk about how CLIP does things. Bring positive pairs closer via data augmentation, right? So if you remember each data, images, right? You're starting to you generate a batch. Each positive, you do data augmentation. They make it a positive pairs. There's negative pair by random sampling different images from your batch. So basically, this is how the positive negative comes on. And then you do a contrast learning about this positive versus negative. High similarity for matched pairs, low similarity for mismatched pairs. So you are actually learning similarity. And the same CLIP also learns similarity. Similarity usually is cosine similarity. If you recall that, cosine similarity will be the one which will be used. CLIP applied this idea to image text pairs. So it's multimodal. Multimodal, one model is image, and one model is text. You can image embedding, right? Image embedding can be CNN, but it can be transformer. We already see how the transformer does the embedding. And the text, you can also embedding. Of course, you can do a bird, for example, embedding your text, right? And then you have two vectors. You're just doing the cosine similarity of these two vectors, then forms the similarity. And basically, just using this one, using similar ideas to train. Change the supervision, right? So standard supervised image net require image to label from fixed vocabulary. This is CLIP instead of learn is image text, right? Pairs are collected at a web scale. So you can collect this kind of image annotation. This one is whatever the annotation those are, right? Of images, learn at web scale. Basically, supervision broader. Because you are changing web scale, it doesn't. It's not entirely classification in the traditional sense, but you see a lot of association image text. And because you see that, this is where you actually can answer questions, just like a pre-training text-only model. This is training image text association alignment. You can answer this about the image, what text should be associated with that, then you can be a class. So this is how it achieved later on open domain classification. Supervision much broader than and this one, right? Language can be reused at test time to specify new tasks than languages. So this is the failure of pre-training beyond the text. Basically, starting from text pre-training to image text pre-training. Okay. 400 million. So this is where roughly the size. I mean, similar to the Google's VIT size, right? VIT is, but it's there for classification paper. Here is for image text alignment paper. This one can be more general. Basically, can be a description of the image. So it's slightly different than classification. So there is two things later on, just sort of why they use contrast learning. So that's explain why they think. Because there's another thing is talk about the image to text translation, which will be the capturing. So this is something. Natural language itself is because you see much more information about than a class, right? Broader than fixed, say 100. And this one also harder to get if you say predefined. Also, if images contain more than one data, then it's very difficult. Basically, there are various issues. So natural language, you do see a lot of much easily to get more papers, more of these supervisions, and yeah, it can tie to your supervision to language more directly. Basically, the same model can be applied to many tasks by changing text prompt. And this is how actually in the provide notebook, it have specifically shows some examples. The examples just show how the text prompt. Basically, you just say, is that a photo of a car or is that a photo of a cat? Then this one classify car versus cat or something. Yeah. So it will ask you some questions, and how this is classified. Basically, you're embedding these two different embeddings and just do a similarity match. Here is architecture. So architecture about you have a text encoder, you have an image encoder, right? So image encoder, this one can be a VIT, could be a CNN. In the original paper, it used both. And then, but let's say it's VIT, get you, each one is a vector, right? This one gets you a vector of the whole image. This text encoder gets your vector, let's say your bird, get you a vector of your text, right? So essentially, you see a pair of this guy, I2 versus T2, I3 versus T3. So these are the positive, this one. Let's say you have a batch of size n, right? This is your batch. These are the positive, right? The other one, all the alpha diagonals are negative. They are not aligned. Okay, so basically, the clip architecture says I have a batch of n image text alignment pairs. When I do this alignment using contrast learning, you have a positive, you have a negative. The diagonal will be positive. Off diagonal will be negative. So that's essentially the idea. And by using that, you are not directly estimate the labels. You are estimate the contrast between the positive and negative. So this is contrastive learning, right? And create data classifiers. Because you already have this positive negative pair, we know that for each one, right? Image, I can say which one should be the closest. Then each one you can think about the logits of n, and this one is the correct one, right? So you can form a softmax. Similarly, the other direction is also okay. So this one is just say image, I will classify to text. Alternatively, I can say I will text classify to image, right? But here is how that's actually encoded when you do the open domain classification. You can ask if you say, oh, I don't know what I've trained, right? I have something I want to differentiate the data, right? Car for your car data, right? Certain cars, let's say BMW, right, versus Toyota. Then you can say it's a photo of BMW or it's a photo of Toyota. This one gets embedded into text. Once you get embedded into text, you can compute which is closest to your embedded text, your image. Then you basically answer the retrieve the classification. So yeah, so basically this open domain classification. When you do VLM, it can do even more than classification. You can do question answering, you can do other things. This we will talk later, but essentially here is something. Encoder, ResNet or VIT. Nowadays, people probably using VIT more. Text encoder is a transformer, right? And the image encoder can also be a transformer. Both map to the shared embedding space, right? The other thing I want to say is this one gets the idea. If you think about generally what happens with this kind of learning, multimodal learning, right? Multimodal learning, one say the individual modality, we do embedding. One of the common idea about how this embedding should behave is particularly like this clip, basically shared embedding space. Meaning this embedding, I can represent both image or text. They go to same. And similar images should be together, right? Similar text should be together, but also image text similarity can be measured just by using the vector. So everything mapped to the same. Everything can be computed with dot products, with a cosine measure, so that essentially you can compare across modality. So this is one of the important ideas which are coming out. This is not unique to this, right? This is a common idea coming out. This one is just say, how do you train this embedding space using this particular contrast learning thing? Training objective match image text pairs should have high similarity, mismatched should have low similarity. So that's basically all it is, and this is across modality. You can do that with text, you can do that with image, you can do this image text. Or other modality, even you can, including additional modality, is possible, right? So why contrast of caption prediction? This is one question they were trying to say. Of course, you can say, I predict the caption from an image that I can form an image representation. This certainly could. The only thing is, if you think about how the internet created, they are free-formed, they are not well curated, they just have, basically they are inefficient. Texture diverse are very noisy, and exact generation is harder, especially it's a free form. Yeah, you don't even know what these are, matching paired and image text. So contrast learning is a much easier, more stable way of doing that. Just make it just looking at the embedding rather than generation, right? I'm not generating the text. I'm just looking at the embedding and looking at essentially both are encoders, looking at the outcome of their encoders instead of a decoder, right? So basically, this would be a different design, starting from an image encoder to text decoder, right? But here you just say text image encoder using contrastive learning. Okay, so this is the design. This is easier to train. So clip predicts which image goes with which text in batch rather than generating the text itself. Of course, nowadays LLM things can be different, which we will talk later. Although we are talking about the way we talk about mostly fine tuning, but one could revisit the multimodal in different ways. Once you understand this, all the possibilities, right? Can revisit something. But at that time, the clip is something good. So clip predicts which image goes to which text rather than generating text. So there's a simpler problem doing an image encoder than the text generation. Clip objective. So let's look at the clip objective, right? So this one is pretty standard. We already talked about that. When we look at you look at the picture, you already see, right? It's a batch of n image text pairs. Compute the image embeddings, right? This one is say using VIT. Text embeddings, say using BERT, right? Then you align. You form a similarity matrix. This is a cosine. This is basically cosine, right? Okay. Actually, that something is I don't know why it's exponential in tau. I think there are some hyperparameter here. Yeah. Or actually should be. I think that there's something wrong. It should be tau exponents here times tau. Yeah, instead of exponential in tau. I think there's a mistype here. Yeah. But anyway, so it's just scaling. Yeah, you scale because contrast learning there is a scaling. Right? Yeah, something. I'll fix this typo. Yeah. But anyway, but essentially you add a scaling here, right? Cross entropy in both directions. Essentially, this guy says I want to use image to predict the text, right? Just looking at normalization over text, right? For each image I normalizing for each text, and then compute this basically each row-wise normalize. The other one is text to image, normalize over all the images, and go over all the text. So basically, you just column-wise normalization, and both adding together, this is your loss function. So basically, loss function will be row-wise and column-wise contrastive loss. And this one will be your, like the logits, right? So this one, you have a logits of size n by using this. Yeah, so basically, this is pretty straightforward, pretty easy to understand. This is basically how it works. If you think about the contractive loss, right? Usually in the original paper, contractive loss paper, we do not do II because II is identity, right? So II. But here II is okay because one is vision, one is text, so they are not identity. So basically, we keep that all in the basically then that yeah. So I think that's pretty straightforward. The representation align image with language that describe that. And this kind of laws seems to appear different time, right? This kind of also appear in attention. This, but then when you take the log, it's a softmax, and then basically this one is pretty much used for at least for training this kind of contrastive learning. It's pretty convenient if you think about it. You just need to form a positive, negative. This one is not in the classification space, but in the embedding space, the dot products, right? So basically, that's all. So once you have this loss function, you just go through that to the training, right? So basically, that's what we will talk about. There are not too much to say about this, except this one just a little bit fixed. It's basically classification. You can think about incorrect and there's correct pairs and incorrect pairs, and you just for each image. I think this one just repeat just treating matching text as correct, treating other text as incorrect. Systematically for each text, you're also doing the same and etching each other image for the negative, and so on. Yeah. So basically, it's kind of like treating this as classification. Yeah. So I think that's about it for this contractive loss. It's a again, the main idea here, if you think about what it actually does, right? If you look at it doesn't really depend on VIT, it's depend on the embedding. But the main thing is it's the key I think is you want to embed different modality into the same vector space, so that their similarity can be measured by cosine. So all the models go to the same embedding space. And with the cosine as their similarity measure. And then once you have that, this comes pretty natural as one of the ideas. How do you train that? Okay, so this requires image text pair. There are other unsupervised image this actually works very well. So people use that for image text, especially for use for the VLM, in the sense of this align image text, and VLM is basic vision language model. Align well with the language model. Use a language model to understand the images. But there are other methods which doesn't require image text pair. They just look at the image itself and do unsupervised learning. We will not cover that. Those are also image representation learning. It's a different way. And they can also learn good image itself instead of image text alignment. So zero-shot classification. One thing about the clip, actually I already mentioned earlier, is can do zero-shot classification, right? So this one, we just trying to do more specifically. So after pre-training, clip turns the classification into text matching. So because the image can be actually not only the image, you can also ask the more specific for each patch, right? Each patch has its own embedding, but essentially the whole image has an embedding, and you can match that for all the text embedding, whatever text you get, right? So basically, the prompts you can have, of course, you can use other prompt, an image of whatever, or a painting or whatever. But essentially, you just describe a prompt like this, for each classes. Given arbitrary classes, you get this, right? And then you get this. And then you can actually answer the questions, which class it is in. This is still for classification, right? The other things, of course, you say, what is contained in this image, right? That is a little bit tricky for this, and it will be easier actually to answer that. It could be do with CLIP, but it will be easier to do with this called PLIC plus LLM, VLM, which we'll talk next time, right? That you can do even more free form. But this one is just already, you do not need to train. The point is you have these classes, right? I do not need to train a classifier. I just ask CLIP. If I have this classifier with, for example, cat, then I just replace it by prompt. And then with prompt without retraining, I just, and then I just, ask these prompts to the CLIP. CLIP will give you an answer. Right? Encode the image once, encode each class prompt, choose a class whose text embedding has the highest similarity with the image embedding. Yeah, the notebook has this example. Basically, if you look at the notebook, which it has specifically implemented this guy, just have an illustration. Load the clip, and then CFAR actually using the CFAR text, right? And then have this kind of prompts, and then you just check, and you can see that, yeah. Natural language become a dynamic classifier ahead, so you don't need to train. So this is a so-called zero-shot classification. It will make it a closed domain to an open domain. Open domain means you can do whatever the other classification. But it's not as free as what you can do with a visual language model. So this is something we will talk. And this one gets you even more broader question. You can do question answering. You can do ask whatever about the image. They will start to answer. Or you, for example, you can say whatever, right? Does the image contain something, right? And so on. Yeah, we will see how that is done. So that will connect back to the language model part. Yeah, so basically, but this one is important. This one, the clip will be regarded as an image representation, which can be used later on. So we will still need that. Prompt engineering, this one really, it's just zero-shot performance, certainly depend on how the classes are verbalized, right? I think you can say dog, you can say photo dog, and it matters a bit. If you recall the clip, it's not trained by LLM. LLM, right? Prompt is even more important because you need to form sentence, real sentence, right? For clip, because the internet annotation of image, you don't know what they are. They are not necessarily a full sentence, right? They're not probably a segment, right? So it's and they have repeated keywords, could be, right? So it's really embedding. It's just embedding. So essentially, if you look at the clip, also they are using with some kind of diffusion model. While looking prompt, it matters, but somehow it's not very well-formed sentences. You just give some keywords sometimes. When they present that, that helps, right? CFAR, because they are all photos, you're adding photo could be helpful, right? For some of these kind of CFAR image nets, right? If you have some others, you can describe something. Basically, you're adding some keywords, which can be helpful, essentially, helpful for these prompts. But it's not as rigorous as a language model. So you can also do the multiple ones, right? If you don't know, you do an average. And this one usually, I mean, those are pretty standard. It's like a language also has. So we didn't talk too much about that. When we prompt engineering, there's something called consistency. You generate a different time many times, and then you average the results. And this often is helpful. shows prompt engineer got noticeable gains. So we will do not want to get too much details on that, but basically this is something which is talked about there. Here is their results, right? So zero-shot transfer. So basically, yeah, their results is learning yeah, I think their title is. So this CFAR, there are some other data sets, right? There's eventually people create a lot of different classification data in the earlier days. Nowadays, probably not anymore, but they have a flower, they have different classification data. And then they just taking a look at this different classification data. Clip actually, this is clip VIT, clip ResNet, and this is a ResNet, which directly, I believe this ResNet is probably pre-trained on the, yeah, I forgot it's a ImageNet and fine-tuned on this. But essentially, you know, yeah, you look at these results, Lucas, in many cases, right, this one can be better than the ResNet results. So zero-shot across many without data-specific training beats supervised linear probe with ResNet on many data. This one is you need, once you have ImageNet trained data, right, ResNet, you really have to do a linear probe in order to train on the specific classification. It's not open domain, right? So, and then for some of that, they do better. For some others, these do better. Yeah. So basically, this is the claim. Yeah. Certainly, I think for some data, probably, yeah. So. But probably what happens is they are not well covered by these. Some of those probably not well covered by the internet. I know some of the data, like Kitty's self-driving, probably not well covered by this internet they are trained on, and then that's why there's a gap. If they do see a lot of things in the internet which covers, then they will be good, right? Robustness to distributed shifts, basically, yeah, I think that's basically a conclusion. So there's some quick conclusion about what they are really matters. So this one I mentioned previously, which is worth re-emphasize. Clip is not only a classifier. You shouldn't treat that as it's more about text alignment, image text alignment, joint embedding of image text, so that they can talk to each other, right? Image talk to image, they by similarity. Text image, you can text and text similarity, and text image also can be done by similarity. So they are all similarity based. So this is and then you can generalize this. Align whole image, patches, and so on. This one, particularly the next lecture, we talk about the VLM utilizing this particular structure. So they essentially can think about you translate the image into text in the embedding space, not in the precise space, but in the hidden representation layer space. It essentially image token really becomes text token. Highlights, router zero-shot, many, this is important, right? Improve performance. And so it's actually strong image representation. It still have some shortcomings. If you look at for some classification doesn't do well, which means the representation probably doesn't see some of the text or doesn't see some of the images in there, at least the data they are trained. So they are not covered enough. But you know, you can add those images in, then you can actually improve generally, yeah. Here is the Python code. Python code for that. So we will essentially again you have a processor which you need, right? So this one is it's a open clip. Lion is this very big open source image data. You can train for diffusion model. You can train for whatever like this. So they train something like this image alignment. Processor is from this model, right? So autoprocessor from pre-trained. Yeah, basically this one gets you how you should process the image, right? This is a Hugging Face. This again is Hugging Face model will be yeah, basically model name, basic clip, right? And the model is essentially this one, yeah, you can process the text, right? Here is input is a processor means a text of essentially this is embedding the text, right? This is embedding whatever the image, and this one get you. So that basically, you know, you have yeah, you have this you have this processed, okay. And yeah, basically, you know, you can get image embedding from this. This is just one way to illustrate that. But essentially, you know, all these multimodal, you also have for this processor. You just map this data to be the right inputs so that model you can take. Because multimodal data, if you think about that, it's a can be arbitrary, right? Image are pixels, this text you need to tokenize and so on. So processor handles this all so that you can actually do that with images, right? So basically here is image embedding, here is text embedding. This one is using the model. This model is a clip model. You can, clip model certainly has both image embedding and text embedding, right? So one you think about the VIT, for example, the other one is a bird, whatever the transformer you have, right? And then you get this. So yeah, so essentially that's all. That's how it's used for this kind of and the notebook has more examples, more let's say it's a more concrete example, basically just going through this. The simple example, it's just a text, but then you know how it's used. So summary, right? So if you think about we talk about here, the few lessons learned, it's a simple lesson, but you know it's a useful lesson. A pure transformer works well for vision when trained at a scale. The scaling law, it can overcome CNN in terms of inputting less restricted in terms of image prior, but learns more. Pretty sure it learns global information, right? So more directly. So this is a VIT. And also it's a simple modification of transformer with just replacing the token, discrete token embedding using a linear projection. Embedding itself is also linear projection, right? So this one is also linear projection by image patch. So patch become token. So that's the only thing you need to remember for that. And also the other one is scaling law. Clip is another thing. Clip is natural language supervision can give produce a broad reusable visual representation, enable zero-shot classification, but in particularly, it's also image text alignment. If you want to say, I want to align my image to text, clip is one of the standard model to do that. For example, when you do diffusion model, you want to say, I want to generate some prompt to ask them to generate questions. What kind of encoder you want to use? You want to use clip because that one map directly to the image. So it's very natural to do that. And the same is others. Yeah. Same for the VLM. This one is commonly used for those. Yeah. When you need image text capability. Together, you know, they basically from fixed label recognition towards a foundation model, right? Bigger. First is bigger, pre-training. The second is instead of a pre-training on classification, I should pre-train on text image pairs, right? So, and then this becomes more towards a foundation model. And the next step, of course, will becomes connecting to LLM. right? So that is next natural because you already see how to scale that image. You already see how do you make it image align with text. This is a simple alignment at the embedding space, right? Then how do you want to transfer this embedding more directly to the LLM? This will be the next. And certainly, you can train image. We will talk about it next. Then we'll see at least how the architecture works. Then clear there are a lot of other variations you can talk about. But for the next time, we'll talk about the open source versions, right? Also the pretty well-known one, Lava, which is a vision language model. How you tune a clip. Clip can embed your image. How do you turn that embedding so that LLM can understand? Right. So basically, this is the topic. Then you becomes a foundation model. You can become a multimodal model. So yeah, so that's all. That's all about the OpenClick is probably what you can use as a implementation of clip, as we see. And next time we'll continue. Next time, basically, the topic will be the VLM, right? So just a broadening clip, and then we'll talk a little bit about the generation using transformer-based generation. Okay, thank you. Yeah, so that's all.